Hi classmates and to our faculty in charge, Ma'am Michelle and Kalubakib. Good day everyone. Today I am going to discuss my presentation about my chosen research article entitled Impact of Nitrogen and Green Manure on Yield and Quality of Sweet Potato in Sandy Soil. A Brazilian case study by A.M. Fernandez et al. From Sao Paulo State University, Brazil. Published by Science Direct Elsevier and the Journal of Article and Food Research, retrieved from www.journals.elsevier.com/Journal of Agriculture and Food Research. Before we start to the prescribed format of the presentation, I would like first to show you some key points of prelude to questions to give us an overview and convey about the contents of this article. These are the questions. First, how nitrogen affects the quality and yield performance of sweet potato at different rates of applications. Number 2, how the previous legume cultivation improved the yield and quality of sweet potatoes. Number 3, what particular amount of enriched application is effective to achieve higher levels mineral contents in storage roots. And number 4, what management practice or intervention should adapt based on the result of the research to attain its benefits to improve the yield and quality of sweet potato. So now let us move to the proper format of the presentation. For the introduction, sweet potato, Ipomea batatas L, is an important source of food in many countries and produces a large amount of energy per day, comparable to cereals. Sweet potato is the fourth most cultivated vegetable crop in Brazil, being grown in all regions of the country, especially in South and Northeast Brazil, where its consumption is higher. The main form of consumption of sweet potato in Brazil is cooked, but the production of chips and flour has started in some Brazilian regions. However, the problem in Brazil, sweet potato is grown annually on 57.3 thousand hectares with a production of 804,000 tons with an only yield of 14 tons per hectare, which is relatively lower than the potential yield of greater than 40 tons per hectare. In addition, N fertilizers are expensive to farmers, loss of quality of nutrient composition in storage roots due to incorrect management practices and high rates of applications that leads to pollution to the environment through leaching. Thus, a hypothesis and a research study was made designed to assess that green manuring, proper mineral and fertilization and management techniques that will increase the production, yield, and quality of sweet potato tubers and improve its nutritional composition in storage roots. Hence, a field experiment was conducted to evaluate the effects of mineral N rates on the yield, morphological traits, quality, and mineral content of the storage roots of sweet potato grown after different green manure sources to possibly solve the current issue. Next is the objectives. Generally, the main objective of the research was to evaluate the effect of green manure and N fertilizer rates on the yield and quality of sweet potato. It was also aimed to assess that green manuring can increase the content of minerals and improve its morphological traits in storage roots of sweet potato, and to find the best combination of previous legume cultivation and mineral N rates in sweet potato. For the methodologies were composed of the materials and methods. For the materials used, for the size of experimental area was 8 meter wide and 20 meter long. For the site, it was established at São Manuel Experimental Farm of the College of Agriculture Science at Sao Paulo State University, Brazil. For the type of soil, it was sandy textured oxysol. For the variety of sweet potato, was CV canadense with a development cycle of 150 to 180 days. 3 months old cuttings of 40 cm long with 8 internodes. Planting distance of 0.30 meter by 0.80 meter per hill at a depth of 10 to 12 cm. For the species of legumes, 8 kg seeds of Shovi crotalaria and 80 kg of velvet beans. Type of fertilizer used at green manure, 100 kg of simple superphosphate and 120 kg potassium chloride in the first year and 60 kg in the second year. The phosphorus and potassium application rates were based on the soil analysis. At experimental plot, urea was used with a fertilizer grade of 45%, split at 50% at planting and 50% at side dressing. The starch and total sugar contents were determined by colorimetric method. Oven was used to determine the dry matter content. Muffle furnace was used to determine the ash content. Nitric perchloric acid solution to digest fresh fiber content. Spectrophotometer was used to determine mineral contents on the digested solutions. SysVar statistical software was used to analyze the ANOVA, and XLStat software was used to perform principal component analysis and correlation tests. For the methods used on experimental design and treatments, the experimental design implemented over 2 agricultural years was randomized block using Latin square design or LSD with a split plot scheme and 4 replications. The main plots were composed of control and 2 previous green manure cultivation, the Shovi crotalaria and velvet beans, while subplots were represented by the end application rates of 0 kg per hectare, 50 kg per hectare, 100 kg per hectare, and 200 kg per hectare. The main plots were 8 meter wide and 20 meter long, and each subplot have 4 meter long rows of sweet potato spaced at 0.80 meter apart. Only the 3 central rows of the subplots were considered available for the evaluations, ignoring the 0.5 meter at the beginning and at the end of each sweet potato row. So to picture out the subplot design, this is it. Next, on the management of green manure and sweet potato. First, green manure species were sown manually on September 5, 2014 in the first year and September 17, 2015 on the second year. In the control treatment, indigenous weeds were emerged from the weed seed bank of the soil. At flowering stage of all green manure species were mechanically incorporated in the soil, their biomass. Next, sweet potato planting occurred on January 15, 2015 for the first year and December 15, 2015 for the second year. Cuttings were taken from the apices of plants from a young crop of 3 months old. During planting, 3 to 4 internodes from the base of the cuttings were manually buried to a depth of 10 to 12 cm at the top of the hills. Side dressing and fertilization was carried out in each treatment on March 4, 2015 and January 29, 2016 in the first and second agricultural years. The sweet potato crop was grown without irrigation, and all the recommended agricultural practices were carried out as needed during the cycle. The harvest occurred on June 22, 2015 for the first year and May 7, 2016 on the second year. On data sampling and evaluations, all the plant biomass and nutrient content of the main plots were gathered. At sweet potato harvest, storage roots from the two 1.8 meter long rows composed of 12 plants were collected in the studied area of each subplot and brush. The storage roots were classified according to the demand of fresh Brazilian market. Thus, storage roots with defects, crook roots, and weigh a greater than 800 gram or less than 80 gram were considered unmarketable. After the classification, the storage roots were counted and weighted, and the number of storage roots per plant, incidence of storage roots with defects, storage roots mean weight, and total unmarketable storage root yield were calculated. The storage roots from each field subplot were used in the laboratory analysis and gathered the dry matter content in the storage roots, N content, total fiber content, mineral, crude protein, ash, and starch content respectively. The Kedal method was used to determine the N content using factor of 6.25 to the conversion of crude protein. The total fiber content was determined by gravimetric method using the methodology proposed by the Association of Official Analytical Chemists, or AOAC. Flesh contents were digested with nitric perchloric acid solution. From that digested solution, mineral contents was determined by spectrophotometry, and the results were converted into 100 gram fresh weight. On statistical analysis, the SysVar statistical software was used for the ANOVA, and XALStat software for the principal component analysis and correlation tests. For the main effects of green manure, the means were compared using the LSD tests at p-value of less than or equal to 0.05. The N rates were analyzed using the regression analysis at p-value of less than or equal to 0.05, and the figures were plotted using sigma plot 10.0 to analyze the significance of green manure and N rate interactions. The green manure means were separated using Fisher's protected LSD test at p-value of less than or equal to 0.05, and the regression equations were adjusted to the green manure species separately. We now move to the results and discussions. For the results of this research, there are 4 key factors were discussed. These are the number 1, the morphological traits and yield of storage roots. Number 2, the quality traits of storage roots. Number 3, the mineral content of storage roots. And number 4 is the principal component analysis. For the morphological traits and yields of storage roots, based on the results of the combination of green manure and fertilizer rate interaction, it has a significant effect on the number of storage roots per plant and total storage root yield. So at the 0 N application, in all treatment, there was an increase in the number of storage roots per plant and storage root yield on the previous cultivation of showy crotalaria and velvet bean. as compared to the control. When high-end rates were applied, the number of storage roots per plant in the velvet bean treatment was greater than in the control. Total storage root yield was similar between all green manure treatment at N rates of 100 and 200 kg of N per hectare. N application increased the total storage root yield in the control, showy crotalaria and velvet bean treatments by 62.8, 27.8, and 17.8%, up to 142, 123, and 140 kg of N per hectare, respectively. Previous showy crotalaria cultivation reduced the incidence of defects and the yield of unmercatable storage roots compared to the other treatments. So the mean weight of the storage roots was affected by N fertilizer rates alone, with a linear increase of 13.2% in response to application. For the quality traits of the storage roots, the N fertilizer rates did not alter the starch content of the storage roots in either legume treatment, while the control, there was an increase of 17.1% to the rate of 126 kg of N per hectare. At N rates above 50 kg per hectare, the starch content in the storage roots was similar between all green manure treatments. However, at N rate of 0 and at the highest N rate, previous showy crotalaria cultivation increased the starch content in the storage roots compared to the control. Without mineral N supply, both legume treatments showed higher storage roots fiber contents than the control. The N fertilizer rates linearly increase the ash and crude protein contents of the storage roots. For the mineral content of the storage roots, N fertilizer rates increase the content of calcium and zinc in the storage roots up to 133 and 141 kg of N per hectare. However, the phosphorus content in the storage roots linearly decreased with an increasing N application rate, while the iron contents were reduced by up to 106 kg of N per hectare. The manganese content of the storage roots was affected by N fertilizer rates alone. The manganese content of the storage roots increased by 18.9% up to an N fertilizer rate of 137 kg per hectare. Only the green manure factor affected the copper content in the storage roots. The highest content of copper in the storage roots occurred in the velvet bean treatment, while the lowest content occurred in the control. The green manure and N fertilizer rich interaction had significant impact on the manganese contents of the storage roots. In the control, the N application rates did not alter the manganese content of the storage roots, while the velvet bean treatment, the manganese content increased by 20.8% with N application. For the principal component analysis, the PCA considering all the treatments revealed that two main components, the PC1 and PC2, were responsible for 54.4% of the variance. Interestingly, this analysis showed that treatments located in quadrants 1 and 4 showed higher numbers, yields, and mineral contents in the storage roots. These treatments mainly group the management with previous cultivation of legumes combined with the application of 100 or 200 kg of N per hectare to sweet potato. In contrast, quadrants 2 and 3 group the treatments that had storage roots with more defects and contents of total soluble sugar, iron, and phosphorus. So now we are moved to the discussions. Based on the discussion of the research, revealed that the most significant finding of the study is that the previous cultivation of legumes combined mainly with the application of 100 or 200 kg of N per hectare in sweet potato improves the yield and quality of the storage roots. Current findings have also shown that showy crotalaria and velvet bean can contribute to greater storage root production and better storage roots quality when combined with the supply of mineral N. Also, the previous cultivation of showy crotalaria reduced the incidence of defects and yield of unmarketable storage roots. Previous cultivation of showy crotalaria improved the contents of ash, starch, phosphorus, iron in the sweet potato storage roots, and both legumes increased the fiber, protein, and zinc contents in the storage roots. The green manure biomass left in the field favors nutrient uptake by sweet potato grown in succession, increasing the nutrient content in its storage roots. The application of mineral N can increase the content of protein, ash, calcium, magnesium, and zinc in the storage roots. The PCA indicated that increase in the N rates in areas without previous legume cultivation has a positive beneficial effect mainly on the total soluble sugar content of the storage roots. Thus, the study indicated that it is possible to improve the yield and some quality traits of sweet potato by adopting management practices that combine green manure and N fertilization at rates between 100 and 200 kg of N per hectare. And for the conclusion, the study concluded that it is necessary to combine green manuring using legumes with the application of 100 or 200 kg of N per hectare in sweet potato to improve its yield and quality of the storage roots. The use of green manure and N fertilization does not promote improvements in all quality traits of sweet potato storage roots, such as the content of the phosphorus and iron. The PCA results revealed that in treatments with previous showy crotalaria cultivation, there was a low incidence of defects in the storage roots, and the increase in the N rates in an area without previous legume cultivation had positive beneficial effect mainly on the total soluble sugar content of the storage roots. For the critic, overall, the study was impressive and highly recommended for actual field trials on hectare basis. Its objectives were attained based on the result and analysis of the study. Results are well explained with detailed support data. The statistical tools used were advanced and reliable. The plan, design, and establishment of the research were properly implemented within an impressive of 2 agricultural years. However, with regards to the methods, one that I emanated into my mind is the number of how many days are the legumes incorporated into the soil at the flowering stage, and why that stage of the plant should be the time to incorporate into the soil. There should be back literature cited with this key point to understand the timing of cultivation at that growth stage of the legumes. And one thing more is that the legume species used must undergo plant biomass mineral analysis to determine its mineral content. Especially, they are commonly called nitrogen fixers. Lastly, there should also be a soil chemical analysis made after the experimental area has been incorporated with green manure.